All right, so we're doing Ohm's law and electrical power. So let's define some things real quick. So we have current, electricity. And so this is when charges.
Wait, are you recording?
Yep.
Oh, it's so awkward.
Charges, which are electrons, they flow through a wire. So charges flow through a wire. Okay, so that's just plain old current electricity. Okay. Current. This is denoted by a capital I in a formula. It is a capital I, okay? This is the rate of flow of charge. I has a formula. We're not going to use it, but not right now anyway. It's more of a, if we do Faraday's things, we do it, but I'm not going to. But so since it's the rate of flow of charge, think of like a rate of charges per second. So, so the amount of charges passing over time. So, amount of charge passing per, that's a Q. Triangle Q over triangle T. Sorry, my Q invaded my T, and it looks very strange now. Okay, so amount of charge passing per second. Okay. The unit we like to use, we call them amps for short. Really, we call them, they're called amperes. And they're denoted, like their unit, like how meters is a little m, theirs is a big A. Big A is amps, okay? Okay, so that's current. And then we have voltage. Voltage is denoted by a capital V in an equation, or delta V. Delta means just change. And this is called potential difference. Okay. This is what drives the flow of charges. So it basically provides a push for the electrons, okay? We call it potential difference because it's usually measured between 2 points, and it's the difference in the push between those 2 points. It is measured in volts, which we denote by a capital V for volts. Okay, and then you have resistance. Which in an equation is denoted by a capital R. I'm going to scooch it on up now. And this is the opposition to flow of charges. This is measured in ohms, which we denote by this symbol. I think it's an ohm.
Oh, I thought that was like sororities.
Yes, it is a Greek symbol. I think it's an ohm. I don't remember right this second. It's been a long time since I played in Greek alphabets. But when you see that symbol, that just means ohms. It means resistance, that's all. And it doesn't mean you're in a sorority, it just means ohms. All right. resistance depends on
I'd let you in.
Is it your frat?
Yeah.
Thanks. You want to start one together?
the type of material.
So you wouldn't follow me.
Oh my God, stop.
I'm sorry.
The width of wire, the length of wire, and the temperature of a wire. So, for low resistance wires, you want them to be metal, wide, short, and cold. Okay, so these would be wires with the least amount of resistance. Okay? Oops. Okay, there we go. Okay. All right. A current must have a power supply, which means voltage, to drive current. Okay, and if you forgot already, that's the push. So it's what pushes the electrons around through the wire. You have to have a wire to allow charges to flow, and there's usually, you need a resistance to use up the energy. If you don't have a resistance to use up the energy, the electrons flow too fast, everything catches on fire. So, all right. All right, so that's current electricity stuff. So now let's talk about Ohm's law. I'll go to a different page for this. You don't have to, I'm just going to a different page. All right. So Ohm's law is a formula. V equals IR. It's on your formula sheet, so you don't really have to memorize it. Okay? That's Ohm's law. Then we have electric power. So yeah, so Ohm's law just uses the three things that we just talked about: voltage, current, and resistance. Okay? So current and voltage are directly proportional here. Resistance and voltage are directly proportional here. Current and resistance are inversely proportional. Okay, so as your resistance goes up, your current goes down, which makes sense because if your resistance goes up, it's going to resist the flow, and the current is the flow. Okay, so that's kind of what Ohm's law is doing. Okay, all right, electric power, this is the rate of conversion of potential energy to usable electrical energy. It has a formula, and it's on the formula sheet, so you don't have to memorize it. P equals IV, where P is power, and that is measured in watts. which we use a capital W for it, which is annoying because work is also a W, but whatever. So, but this is watts. Okay. There are alternative formulas that you can use for power as well, and they're also on your formula sheet somewhere. Let's see, I had your formula sheet handy. Where did it go? There it is. Okay. Okay, so there's Ohm's law, and there's power. And so these are the alternative things that you can also use. So there's Coulomb's law, there's the charge carrier total, and then we're going to do that one in a minute. Okay, so power can also equal, it equals IV, but it can also equal I squared times R, and it can also equal V squared over R. So all of those can equal power. Okay, and they are on your formula sheet. You don't need to memorize any of that. Okay. All right. So then let's talk about cost. How do we calculate cost? Cost. This is going to be measured in kilowatt hours. Okay, so this is what we measure the cost of energy, and we measure it in kilowatt hours. Okay, or it's technically in dollars per kilowatt hour. Okay, so the formula for that, cost, and it says total, is equal to P times time times, I'm going to go with price. Okay. This is also on your formula sheet. It says P delta V on your formula sheet. I just don't like to write the deltas. Okay. And so in this situation, though, power needs to be measured in kilowatts. So you have to take your power, if you find power in watts, you have to divide it by 1,000 to get kilowatts before you can stick it in this formula. Okay? Time in this one is not measured in seconds. Time would be measured in hours because your cost, or I'm sorry, price, because your price would be measured in dollars per kilowatt hours. And this is what is set by the electrical company. Okay, so in the big Texas freeze that we just had and all the stuff that was on the news and the hullabaloo that went on, the price per kilowatt hour for variable rate plans went really, really high because the demand was really high and the supply was very low. That's not usually the case. So that's why people were very upset that have variable rate plans. Fixed rate plans, nothing changed. You can't change the price on a fixed rate plan. So, all right, let's do an example. All right, so how much does it cost to operate a TV? That's not V. TV, words are hard. With 60 ohms of resistance, if it is plugged in and on, and when you plug stuff into a wall, typically, in our neck of the woods, the wall voltage is 120 volts. That's Americans. We do this. We do 120 volts. That's what's supplied to your wall. Okay. For 24 straight hours. All right, and I'd have to tell you that the price of electricity for this particular TV is 35 cents per kilowatt hour. All right, so we have, let me get the highlighter again. Okay. We have resistance, we have voltage, we have time. I'm going to just put H at the end of that just to make me a little happier. And we have price. Okay, so you can look at your formulas that you have for power, because we need to find power before we can plug it into this equation, right? So if I've got resistance and voltage, okay, then which equation are we going to use? We're not going to use this one, okay, because we don't have current. We could use this one and find current, but it does nothing. Or we could use Ohm's law to find current and then use this one to find power. So you could do it in 2 steps, or you could just pick one of these. What do you want to do?
The last one.
The last one here? Great, okay. So P equals V squared over R. So V squared, 120 over 60. Okay. Oh, let me move that up a bit. There we go. Okay, so you get 240 watts. We have to divide that by 1,000 to get kilowatts. And then we want to find our cost, right? So our cost total. And we're just going to plug in that equation. So power in kilowatts is 0.24. Our time in hours is 24. And our price, I'm going to go ahead and put the dollar sign with it. 35 cents per kilowatt hour. So the kilowatt hours will cancel and you're left with dollars. Okay. So it's 2.016, but this is money. Money goes 2 places past the decimal pretty much always. Okay? So it should be $2.02 because the energy company is pretty much always going to round up. Okay. Okay, there we go. All right. You want to do a quick Ohm's law example? Yes.
If it's on the test, should we always round up, or should we do it based on like normal rounding rules? Like,
Probably just normal rounding rules, but just know as a consumer, the energy company always rounds up. They don't round down. So, all right, I think that's good. The other way we could have done this one, an alternative method, would be if we wanted to use Ohm's law. So if we wanted to do V equals IR, we could find I first, so we could divide both sides by R. So then you could do 120 divided by 60, which gives you 2 amps. Okay. And then P equals I times V to find power. So then it would be 2 amps times your voltage, which is 120, which gives you 240 watts. So that would be an alternative method if you wanted to use Ohm's law. Okay? Gets you the same answer.